Good afternoon, and welcome to the Civil and Environmental Engineering Distinguished Lecture. My name is Khalid Musallam. I'm a professor in the Civil Engineering Department. And every year, the Strategic Planning Committee recommend to the department the names of speakers of our distinguished lecture. And I have the honor of chairing this committee this year. And the committee decided to take a risk-free decision by nominating Professor Armen Der Kiurehegian. Ironically, he's going to talk to us about risk. Professor Armen Der Kiuregian. And that's for the spring lecture. And I'll highlight a few things about Professor Der Kiurehegian because the list is so long and I can't wait to listen to his lecture myself. So Professor Der Kiurehegian have received his bachelor and master degrees from civil engineering from Tehran University and his PhD from University of Illinois at Urbana-Champaign. He has been with the faculty of UC Berkeley since 1978. He holds the Taisei chair in civil engineering since July 1999. And his contributions as an educator are highlighted by his instrumental role as a founder of the American University of Armenia, an affiliate of UC Berkeley. Professor Der Kiurehegian's research revolves around rigorous development and applications of probabilistic methods to solve civil engineering problems. We will definitely hear about that today. Professor Der Kiurehegian has received many honors and awards. I will name only a few. He has received the ASE Walter L. Huber Civil Engineering Prize, the Serra Award of Civil Engineering Risk and Reliability. He is an elected foreign member of the National Academy of Sciences of Armenia. He is also an elected member of the United States National Academy of Engineers since 2011. I would like to close by his most recent award, the 2014 ASCE George Winter Medal. For those who are not familiar with this medal, this is offered to an active engineer, or educator, and researcher who express commitment to other fields than engineering, such as the fine arts. So for those who do not know, Professor Der Kiurehegian is a very well-accomplished watercolorist. He said he learned that from his father, who he claimed he's better than him. But you can see his work in his own website. It's really fascinating and very inspiring to see that dimension of a very well-accomplished researcher. So without further delay, I give you my mentor and colleague, Professor Armen Der Kiurehegian.
Thank you, Khalid. Thank you, Khalid, for the kind introduction. And I want to thank my department and my colleagues, especially the Strategic Planning Committee, for giving me the honor of presenting this distinguished lecture. This is my second lecture I give to this department. The first one was 37 years ago, and you can imagine what it was for. I want to specifically thank my former and present students who are my partners in my research, and they do the heavy lifting, as my colleagues know that well. So on the name of those who have graduated, I would like to ask my current students and postdoc to stand up and to be recognized. If possible, they're all sitting here. Please. work I'll present here naturally is the result of work by several of my students, past and present. So I haven't acknowledged them by name inside. I will mention a couple of them, but this has been influenced by many of my students, so I'm very grateful. I'm also very grateful to the university because the work environment and the kinds of students we get are remarkable here. So I'm very grateful. This is the topic of my presentation. And to start with, I would like to provide motivation through a number of pictures. Modern societies are very much dependent on infrastructures such as transportation, power, subway or train systems, water, gas, sewage pipelines, and energy production systems. And these systems are subject to all kinds of man-made and natural hazards such as hurricanes and tornadoes, earthquakes, and explosions, probably one example of a man-made hazard. The effects of these hazards on infrastructure can be very devastating for society and economy of communities. For example, you will remember during the Loma Prieta earthquake, as a result of this failure on one span of the Bay Bridge, the transportation between San Francisco and East Bay through this bridge was interrupted for more than a month with enormous economic consequences. This is a result of the Northridge earthquake, an electrical substation. This is the Sandy earthquake that closed several substations like this, which were inundated, and of course resulting in blackouts in New York. So how do we mitigate societal losses through decision-making prior to, during, or after a hazard? Some of these hazards I mentioned evolve in time. For example, a hurricane, it takes some time to evolve. So, in fact, there are reasons to do decision-making during the process of evolution of the hazard. Other hazards, such as earthquakes, happen almost instantaneously, so that you really cannot do any processing during itself, except maybe early warning systems. In such cases, then one is interested particularly in during and after, prior and after earthquake hazard. This particular talk will be post-earthquake hazard. My focus will be on earthquakes. Well, if you're an engineer, the kinds of things you need to do are, from my point of view, 4 fundamental issues. First, you need an understanding of modeling of the hazard, the nature of the hazard, be that earthquake or whatever. My talk, though, focusing on earthquakes, it's applicable, the concepts are applicable to other kinds of hazards as well. Then you need modeling of the infrastructure system. Next, in order to make proper decisions, you need information, and you need to process information. And from my standpoint, all information is uncertain. Precise or deterministic information is just one possible extreme case. So I'm emphasizing uncertain information. And you will see in the case of hazards, particularly post-hazard situation, you do have uncertainty in the kind of information that you get, enormous uncertainty. And then on top of all this, you need some kind of a framework for decision making. In my view, Bayesian Network and influence diagram are tools that are ideal for this purpose. They provide an ideal framework. So I will, as an outline, I will give you a brief outline of what Bayesian Network is, but I will focus more on modeling the hazards so you see how the flow of thought goes in modeling something like that. I will talk about influence diagrams, again, briefly, Influence diagrams are Bayesian network with decision and utility nodes added to it. And I'll give two examples, one for decision on whether you inspect or not, whether you shut down or not a component. And then I will give another example for prioritization of component inspections in a system. Then I will apply this to a hypothetical model of the California high-speed rail system. Obviously, emphasis on hypothetical because the system doesn't exist and God knows may not exist ever. So we don't know, but this is a hypothetical model. And there you will see learning with evolving information and learning and risk assessment with evolving information, and then decision-making on a closure of segments of the system and prioritization of inspection of components, which components you want to inspect first and which second and so on. So Bayesian network. A Bayesian network is a graphical way of representing a set of random variables. In this case, a very simple case, I have 5 random variables connected together. The nodes in the graph represent random variables named x1 to x5, and the links represent dependence between these random variables. There is a very nice terminology, familiar terminology. For example, x4 is a child of x1, and x1 is a parent of x4, or x1 and x2 are parents of x3, and x3 is a descendant of x1, and so on. To each of these nodes is attached a conditional probability table that describes conditional probabilities of the child given the parent. For example, here, these are the states of this random variable. These are the states of the parent. And inside the table, we list conditional probabilities. So this is how information is encoded in the Bayesian network. If you go to a node that has 2 parents, then obviously this table becomes bigger. Now you have to list all possible states of x3 versus all possible states of x1 and x2. So you have a 3-dimensional table. And this immediately gives you an idea that Bayesian network could be limited in terms of how many parents you could have, because immediately this can grow if you have many parents, if a node has many parents. This is an issue I will come back later. And nodes that are up there, these are root nodes. They're described in terms of their marginal information. One of the most interesting aspects of Bayesian network is that, as the name implies, Bayes, it is able to process information. Suppose we have information that this particular random variable is in a particular state. Imagine that this is demand on a component, and we somehow know what the demand is. This is called evidence in the terminology. So we enter evidence in one of these nodes. The result is that that information propagates through the network, through the graph, and updates, revises the information contained in each of these other nodes. And there are rules by which we update this, the so-called Bayes rule. This is the only formula, or maybe one of 2 formulas I will have, so don't think that I'm having too many of these. So there is a rule by which this probability is updated. You will note here there are 2 probabilities of this random variable x4, which could be any of these. One on the right, which is prior. This is our prior information about that particular random variable. The one on the left is posterior to having received that evidence E. So this is how information is processed. And there are algorithms that do this kind of analysis. Now, let me, as an example, show you how we construct a Bayesian network model of seismic hazard. So imagine we have some kind of infrastructure having these components 1 to 8 in an area spread out. One of the things about infrastructures is that they're not at a point, they're spread out. So they're exposed to a random field of hazard that complicates matters, and they can be exposed to a variety of kinds of hazards. In any case, it's in a region where we have several potential earthquake sources. So, an earthquake has happened. We don't know which source produced that earthquake. So we have a random variable here called source that has three states. Either it's source 1 or source 2 or source 3, each one having its probability probably proportional to the mean rate of events on this fault. Next, there's a child of this, which is the source. Now, once we know which source it is, then we know the geometry of the source, as you can imagine from here. Next, let's assume that we select the particular outcome from this, which is source 1. Then on that source 1, let's say that the earthquake happened with an epicenter, that is, this is the start of the rupture at that location. Then the random variable that describes the location of that epicenter is a child of this source geometry node. Then to each source is attached a probability distribution that describes the magnitude of the earthquake, and that is dependent on the source because it depends on the size and length of the fault and so on. So you see that is a child of the magnet. And then the earthquake actually happens as a rupture along this fault, this green line. Maybe selection of the line is not appropriate. The color is not appropriate. Maybe it should be more reddish color. But the length of this rupture is random, depends on the magnitude, and the location of that rupture is random along this fault. But it contains the epicenter. So as a result, all these are parents to that node. But you will note that that node is a rectangular shape because that itself is a Bayesian network. Bayesian network is object-oriented, so this actually has a Bayesian network behind it. And this is the object. You see the dashed lines, the nodes are input nodes for this. The solid ones are internal nodes, and the external are the left and the right coordinates of that rupture. So that now we know where exactly that is once you're in that node. But what we are interested in are the intensities of ground motion at the locations of the components of the system. For example, at location 1, we have a measure of intensity at site 1. In earthquake engineering, we have developed, or researchers and practitioners have developed formulas for predicting the intensity of motion at a point in terms of magnitude, distance, and other variables related to the site, and two regression random error terms. One is called inter, this is between, from event to event, and one is intra, which is, for one event, it's an error term from location to location. And as you can imagine, these error terms from location to location are correlated, because if you have experienced higher than the mean ground motion at one location, at nearby locations you would expect higher than the mean intensity. So there's correlation between. As you go farther and farther away, then the two would tend to be uncorrelated. So in a sense, the ground motion is a random field, and therefore these terms are, for different locations, would be correlated. In any case, so I have all those magnitude, source, everything being parents to this. And of course, I have those two error terms, which here, for simplicity, I've just called it epsilon 1. So these are all parents to this one. And this, again, is an object. I'm showing the Bayesian network behind it. Again, we have a number of things that come into so that we can describe this equation. And here I have even included a directivity effect. If this is a near fault ground motion, then you would also have directivity. I will not give the details of this, but the output from this is the intensity measure at that location. Now, of course, I'm dealing with a system, so I have to have also intensities at other sites of this infrastructure system. So, well, I connect all these other ones. I haven't connected yet this one, because remember, this is only for this. I have separate ones for these, and these are all correlated. Well, I replace them by a vector. And it turns out that because of this correlation between them, this is a very difficult matchup to handle with Bayesian network. We have a paper specifically on this issue, and the end result is that we are able to represent it in a form like this with some auxiliary variables. I will not get too much into details of that. All right, so that's the model for the seismic hazard. So here is the seismic hazard model as an object. You saw the Bayesian network behind it. Here is the system performance model I'll describe. So these are the intensity measures at the locations of the components of the system that you just saw before. And here are the states of components of the system. And now let's focus on that. And for this, there is a standard way of handling in terms of fragility, which is conditional probability of being in any one of these damaged states, say intact, light damage, heavy damage, or failed, versus demand on the component. So given this demand, these probabilities described. So in fact, this fragility concept that is well known in earthquake engineering is ideal for modeling in a Bayesian network. It gives you directly the kind of conditional probability table that you need. Next, I will focus on the system performance model. So again, think of our infrastructure system there. If you know the states of the components of the system, then you can tell the state of the system. You have to do a disciplinary analysis. If this is a transportation network, then you need a traffic engineer to tell you that relationship between the two sets. If it's a water distribution system, then you need a hydraulic engineer to do that. In any case, it's something that is described within the principle, within the discipline of interest. But in any case, this concept is described here. If I know the states of these components, then I know the system state. The problem is that this, as you can see, has too many components. Now, this is a very simple system, but you may have hundreds of components, and then this doesn't work. At least, apparently, it doesn't work because the conditional probability table that you will attach here would be enormous. For example, for a system with 100 components, each component having two states, this would have a size of 2 to the power 100. Forget it. You can't store that kind of a thing in any computer. Another way to do is to introduce intermediate nodes that represent so-called minimum link sets or minimum cut set. The minimum link set of a system is the minimum number of components such that if they survive, the system survives. For example, here, 178, if these three survive, then you can communicate between source and link. So you introduce these intermediate steps. Or minimum cut set, which is a minimum set of components such that if they fail together, then the system fails. For example, here, 1, 2, 3, 4 is a minimum cut set. And so you go from there to the minimum cut sets, and from the minimum cut sets, you go to the system. But the problem is that you could have many minimum cut sets or many minimum link sets, or each of these could have many components, and again, you're back to a problem that it's not scalable. So in our research, we have approached this problem in two different ways. One was by creating a Bayesian network topology optimization. Michel Bensi did this by solving a topology optimization problem where we minimize the number of links in the network, in the Bayesian network, subject to making sure that you have counted for all the minimum link sets and minimum cut sets. Another approach that Iris Tien, sitting here, has developed is to minimize the memory requirement by saving the system condition probability table and all the intermediate similar things that you have to store in a compressed form. I will briefly mention this too. For example, the Bayesian network topology optimization, without giving you the details, for the same system, this is the solution, so-called minimum link set formulation. If you look at this carefully, it has a chain structure. So no node has more than 2 or 3 parents. So we are able to easily solve. Here is another solution for the same problem using that was minimum link set, this is minimum cut set formulation. So these are equivalent solutions for this using this Bayesian network topology optimization. The problem is that this topology optimization problem itself becomes huge afterwards. So it's better than not having, but it is not scalable to very large systems. So IRIS's approach is this. We go back to this naive formulation with all the components being parents to the system. If you, for the time being, think of a 2-state system, then these components are either in 0, that is failed state, or 1, that is working state. Then each row, you can look at each row and determine whether the system is in the 0 state or 1 state. It turns out, first, you don't need to store this because the pattern is such that you can have a formula knowing exactly what the numbers are in each row. You just need to store this, but even this is huge. 2 to the power 100 is the size of this if you have 100 components. So what IRIS has done is has used compression algorithms, specifically run length and phrase encoding, to compress this particular column. And then she performs forward and backward. And for forward is when you don't have any evidence, you're just solving for a marginal distribution of the node. And backward is when you have evidence and you are computing conditional probabilities. She is able to perform this without, and this is the challenging part, without decompressing or recompressing these intermediate factors. So everything is done in a compression mode. And of course, this method can be generalized to multi-state components and systems. So here's an example, again, that system, except that IRIS has added some components here or here so that the system size can be increased so we see how it works. And here you can see the memory demand of the existing algorithm. We solve it by the so-called junction tree algorithm. This is the memory storage as a function of number of components, and we run out of memory on a 32 gigabyte RAM memory computer. So we can't go beyond that. But the memory demand here is like 10 to the power 8. This one stays essentially constant. It doesn't change with the size because the compressed information, both in terms of the conditional probability table and a dictionary that you have to carry, dictionary of phrases, those are really minimal in size. You can see here, I think, 150 or so. Of course, nothing comes for free. There's no free lunch, and so we end up spending more time computation because we have to compress this large metrics, and we have to do analysis without decompressing it. So there's more to the algorithm. There's some more additional time. Now, things get much better than what you see here because then she uses 3 kinds of heuristics to speed up the computation. I will not show that. Briefly on influence diagram. As I said, influence diagram is a Bayesian network with decision and utility nodes added. So here, this is a very simple Bayesian network with 2 random variables, this one being a child of that. This one is an influence diagram. This is a decision node. This is a random variable. And the arrow says that the probability distribution of this random variable depends on what decision you make and what choice you make in this decision node. A decision node also has states. The states are option 1, option 2, your alternatives for decision. So the distribution of this random variable depends which alternative you choose. This one is also an influence diagram with only 2 decisions. And the arrow is a precedence arrow, meaning that when we go to make this decision, we know what decision we've made here, which alternative we have selected here. So that's kind of a precedence node. This one is a reverse of this. And here we are making a decision knowing the outcome of this random variable. That's what, so remember, a child knows the state of the parent. So that's what that means. And finally, this is a complete influence diagram where we have a random variable, a decision node, and a utility node. Think of it as loss or benefit or cost, which depends on what decision we make and what is the outcome of this random variable. Now let's move on to an influence diagram for decision making for a shutdown decision of a component. So here is a demand on the component, like you saw before. Here is a component, the state of a component. And here there's a decision node. Do we shut down this component given, there is an earthquake, here's the random demand. Do I shut down that component or not? Well, depending on what decision I make here and what the state of this component is, there would be a loss. For example, if the component is damaged and I keep it operating, I have liability cost. If the component is in good state and I shut it down, I lose function of the component, so I lose benefit. So in any case, there is loss. This is information, no information decision without any information. This is decision with perfect information. When we go to make this decision, because this is a child of this, we know the state of this component. So we're making decision knowing perfectly what the state of that component is. Really not a realistic problem. The more realistic problem is this, where we make an observation. We do an inspection of the component or we test the component. So when we test, we make an observation, and that observation here may not be precise. So no test is precise. These tests are always indirect. So the true state then gives rise to some kind of observation, depending on the quality, the type of inspection we are doing. And then the shutdown decision is made with the knowledge of the inspection result, not the true state. So this is decision making under imperfect information. And now this is one step further. We have two decision nodes. First, we have to make a decision whether to inspect that component or not. Or maybe we have several options here. Do not inspect, inspect visually, inspect using X-ray devices or whatever. So there are alternatives here. First, we have to make this decision. And there is a cost associated with that decision. There is utility associated with that. And then when we go to make a decision on whether we shut down that component or we should keep operating that component, well, then that decision is made knowing what observation we have made and under what kind of inspection. So the inspection is also a parent of this. And then we have, of course, the loss here. The arrow from here to here is because the kind of observation you will get depends on what kind of inspection you do. If you do a very casual, very crude inspection, well, this would have more error compared to this than if you did a very precise inspection. So the conditional probability distribution of this depends both on this and on that. In fact, there's well known in probability risk analysis, there's something called test likelihood metrics that describes the conditional probabilities of the observed state given the true state. And if you have perfect inspection, then this would be a diagonal identity matrix. The off diagonals are indications of crudeness or error in the inspection. Now we put this all together for a system. So you have an infrastructure system. Here's the hazard model that you've seen. Here's the system model that you have seen as Bayesian objects. And this is component 1, component I, all the way to component n. And you see this is the same as I showed before, except that now I have a capacity here because the component may have multiple states. Given the true state and given what we decided about that component, whether we shut down that component, operate it at half capacity or full capacity, that would dictate this node. And these are all coming into the system model, and then that goes into eventually a loss at the system level in case you have to reduce speed or you have to shut down certain links. There is a cost associated at system level on top of the cost associated with the component level. One thing I forgot to say here is that this is a limited memory influence diagram where certain links are not explicitly shown. In particular, we would be interested in knowing after a major earthquake, where do we send the crews for inspection? We have, say, 5 crews for inspection, and we have 100 components. How do we send them? Which components are the most critical? So we would need to have decision nodes between these inspections from component 1 to 2 and between all the components, which means that you would have to consider all these combinations of orders and solve all of them to figure out which order is the best. Well, we couldn't do this, so it cannot be done for a large system. So what we did is we used limited memory ID, which you see here, but then we've used this concept of value of information. Value of information is, suppose you have the expected utility given no information. So no testing, no inspection done. There is a utility associated with the network. And then we do expected utility given information at no cost. Imagine that you do a certain inspection, but no cost associated with it. The difference between the two utilities is what is called value of information. Obviously, if the cost of inspection is greater than value of information, you should tell the inspection guy to get lost. You don't want to buy that inspection. If the cost of inspection is less than value of information, then that inspection is worth doing. The net benefit of inspection, however, is the value of information minus cost of inspection. That's the net benefit. And if you have several alternatives for inspection, then that particular alternative that has the maximum net benefit is the one inspection that you would choose as a decision maker. So we use this to order the inspections in the network. All right, now let me describe the application, the hypothetical model of the high-speed rail system. We consider the segment from San Francisco going to Gilroy, and the segment is color-coded here in terms of the various components of embankment, aerial structure, tunnel, and so on. At least this was how we obtained the information from early studies of the system. Along this path, we have indicated several cities, Millbrae, Palo Alto, San Jose, and Gilroy, where there are stations planned. The idea is that if somehow this segment somehow is damaged, rail system people are very worried about losing customers. So the idea is that if this is damaged, can customers go there and take the train south? Or can you build bridges between these links? And so we're interested in these links. And these points along the line are where we're measuring. These are ends of each of these components. So from there we compute the demand on each of these components. Well, I'm not going to go through all numbers in this table. Just to tell you that what we did, we assumed that each component could be in 3 possible states: no damage, slight damage, which is SD, and heavy damage, which is HD. Then we also assumed that each component could be, we had 2 choices for inspecting each component, either visual inspection with minimal cost or extensive inspection with much higher cost. The columns here are the liability costs. If there is slight damage and the train goes with normal speed, there will be a certain cost. If the damage is heavy and the train goes with normal speed, there will be a much higher cost because this is liability. And but if they under heavy damage, if they reduce the speed, then the cost would be far less. And there's also costs associated with reduced speed. If you reduce the speed of the train, there will be some cost associated with this is associated with each of the links because the speed would have to be reduced for the entire length of the link. And this is the cost of closure, the idea being that this is the cost of losing some passengers and also busing passengers from one station, sort of bridging the link. So that's the picture of the whole thing. Now, imagine an earthquake has happened. Just a couple of minutes later, the earthquake seismographic station announces that this earthquake had a magnitude of 6.8 with an epicenter 30 on Hayward Fault, 30 kilometers from the north end of fault. So we know this information. Here I'm assuming they give this information in a crisp way to simplify the presentation. But more generally, this could in fact be, the magnitude is 6.8 plus minus whatever, and the epicenter is approximately. We could handle that too, but here, precise information. So we get this within minutes of the earthquake. And a few more minutes later, we get evidence case 2, which is evidence case 1 plus that a ground seismogram there has recorded a spectral acceleration of 0.45 to 0.5 g. Right? So this is actually higher than what you would expect from an earthquake happening there. So it's sort of higher, it's bad news. All the evidence cases I'm considering, these are all bad news. So bad news on top of bad news, it'll be easier to present this. And then a little later, we hear that the ground motion at this location had a pulse-like behavior, which would suggest that if so, then the rupture on this fault propagated towards the south. And this is bad news for these components here. And a little later, news comes through a telephone or whatever that a particular component, number 17 down here, has experienced extensive damage. This is also bad news, not only locally but everywhere, because, well, if one component had extensive damage, the earthquake must have been very severe. What's happened to the other components? So that's what we need to know. So now this is the learning process. First, I will try to learn about the nature of the ground motion. I still don't know the ground motion everywhere. But I will look at, I only know the ground motion at site 2 because in evidence 2. So here I'm showing you this probability distributions of ground motion intensity at 4 different sites. 1 there, 6 somewhere there, 11 somewhere here, and 16 down there. And these are shown color-coded for different evidence cases. Evidence case 1, you remember, we only knew the earthquake had happened there with epicenter there, is blue. And you see this is the probability distribution. Then evidence case 2 is that now we have learned that site 2 had a high intensity. What's happened, if you look carefully, the probability mass, the yellow line, has moved towards higher values. Why? Because what site 1 is close to site 2. If site 2 has experienced more than expected intensity, the chances are site 1 has also expected. So it's this random field correlation that we are learning from, right? So, but if you go to the other sites, the site 6, even more site 11, and even more site 16, the difference between blue and yellow is not very much because these sites are getting farther and farther away from site 2. So we're not learning very much from what happened in site 2. Then evidence case 3, remember, was a pulse-like motion and, that indicated that the rupture was propagating to the south. And look here, the green line, green distribution, hasn't changed because that site there at site 1 would not be affected by that directivity effect. There's no direct. But then if you look carefully, and nothing here also, because 6 also is not affected by directivity. But these sites which are down below and sort of at the end of this rupture, so they are optimally positioned for the forward directivity effect, you see the probability distribution shifts towards higher values. And in evidence case 4, well, this thing really pushes, the red one pushes very high, because if we had a component failing, experiencing extensive damage around here, then the ground motion around there must have been very high. So you see the red one shift. So this is showing how we are learning from this evolving state of information. You can imagine that post-earthquake, you will get a lot of this kind of information. If you have a system like this, you can process that information and update your information about the state of the ground motion here. Now I'm looking at the probabilities of failure of the components, from component 1 all the way to component 9. And this is evidence case 1, which was we knew only the magnitude and the location of the epicenter. So it turns out because the earthquake is way up north, the epicenter, there's a little higher probability here. And some of these components are weaker or whatever. This is how we get. Now, evidence case 2, there is unexpectedly high intensity measured at this location 2. What happens is that components near that location have higher probability. The probability estimate of their failure has gone up because of this bad news there. That bad news affects everywhere because, well, maybe a part of this was just this epsilon and epsilon inter event. That is, this was just an earthquake that for given magnitude caused higher intensity everywhere. So that's what is causing this. But this one is the effect of this random field of ground motion. Now, evidence case 3 is added. Now we know this is pulse-like, so the rupture propagator. Now these components in the southern portion are being affected by this information. So this is going up. And eventually, evidence case 4, well, of course, that particular component 17 has probability 1, which is out of this picture. So the scale is not going all the way to 1. But that's really bad news for everyone, particularly all the components that are towards the end of this line. So I hope you see how you can do risk assessment with this evolving state of information. And this is, again, probabilities coded with this, color-coded with the evidence cases of being able to go from San Francisco to Gilroy, from Millbrae to Gilroy, and so on. Of course, the further south you go, the less the probability of not being able to go. So that's what this is indicating. Finally, these are decisions now. We want to we have very few crews, and we want to prioritize to see which links we should first select the links. Well, it turns out that under evidence case 1, link 1 is the highest priority. Again, all 3 cases, link 1 is the highest priority. And in link 4, under evidence case 4, it shifts to link 2 as being the highest priority. This has to do with all these numbers we assume, some of which were quite arbitrary. So it is really not that easy to explain why this happens. These are the second highest priority links for inspection. Interestingly, these are not to be inspected, but you should reduce the speed of the train. Either because inspection is too costly for these, or because the chances of having heavy damage are so small, but the chances of having slight damage are high. So it says reduce the speed, no need to inspect. So at least there's no priority to immediately inspect. And of course here, obviously, you don't want to, in evidence case 4, where you had one of the components of link 4 extensively damaged, you don't want to inspect. You just want to shut it down. And so that's what this says. And within each link, then we have an order for the components within the link to be inspected. Here, for example, for link 1 that goes from San Francisco to Millbrae, it turns out that in all cases, well, you do these problems and then you wish you had done other numbers, but the thesis is finished, so you don't want to force the student to do more. It turns out that our extensive inspection option was too costly. So in all the cases, there was visual inspection. And the priority is for component 1, and then these components 4 and this. And so those are the priorities of components, first and second priorities. Well, just to finish, I hope you will agree with me that Bayesian network influence diagram are powerful tools for modeling, for probabilistic inference, and decision making. The modeling is very interesting. People are afraid of probabilistic modeling because there's so much math in it. But there is an aspect, a transparency to modeling with Bayesian network, which is appealing. You saw that how I was able to model. If I have a seismologist with me who is an expert in that, and doesn't know probabilities, it's hard to find a seismologist who doesn't know probability, but if we do, then they could tell me that, you are not doing the right links. So there is transparency to the modeling that you can work with people who don't even know probability if they know the system well. And you saw that it's a fantastic tool for processing information, uncertain information, and of course decision-making with addition of the influence diagram. I think this can be used for real-time decision support system. My vision is a control room with a big screen with layers of Bayesian network, where after an earthquake, the managers of this infrastructure system do the assessment. Of course, you don't want the machine to make decisions for you. This is decision support system. It tells you what the numbers are, what the priorities are. Now, you could select that. You may have reasons to go some other way, but at least it processes the information in a logical way, and you realize that human brain is not able to process the large amount of information that you would get after an earthquake. This can be used also as a mitigation prior to the hazard, during the hazard, or post-hazard. One caveat is that in order to use it in this context, you really have to anticipate what will happen to model it. Otherwise, for example, if you didn't model a component, you don't know anything about that component. Right? So you have to anticipate what will be the case. So one can do this by learning from past events and develop models. And I think this is a very fruitful area to do research, and so I would encourage particularly our students to look into it. Well, thank you very much. I'm very grateful to you. Yes, myself.
Thank you, Armen, for a very fascinating presentation, especially for some of us like me who really always figure out it's all intuitive, but really this is showing that you can make decisions based on facts and mathematics and science of it. My question is, in your presentation, you put a lot of emphasis on that initial data that's coming to you from visual inspection. And I'm thinking that if earthquake happens today, where are those visual inspectors going to come from? In fact, you need hundreds and thousands of people immediately after earthquake to do those inspections and report to you. I cannot make my decision on someone looking at a bridge and saying, oh, I see cracks. And in fact, some of the most important damage that we saw during Northridge, which was the crack in the wells, was absolutely invisible. You had to take the fireproofing even out. So why not that first decision-making come to you automatically by having enough instrumentation, certainly our group, even our faculty in civil engineering has worked on this, that automatically that comes to you. So even if the earthquake happens at midnight, how they are going to inspect visually? So the project that you studied is multi-billion-dollar, maybe trillion-dollar project. Why not have instrumentation that will automatically send signals to your decision-making network, and that data will be precise because that's the instrument, and that doesn't depend on visual inspectors, human mind. That's my question. Why to rely on visual inspection, not instrumented data coming to you directly?
Yes, thank you for your comment, Hassan. I think I mentioned earlier transparency, that experts can tell you whether this is a good model or not. This is a good example. Maybe you should call it something else, not visual inspection. We called it visual inspection as a cheap alternative for inspection. But you are perfectly correct in that this model is ideal. Maybe I should have stressed more. This model is ideal for a situation where you have sensors all over the place and you're getting sensor information. Here the sensor was the seismograph. So we had one sensor and maybe the other sensor that sensed a pulse-like motion. So I'm envisioning, yes, instrumenting all of this. If you wish the visual, you can translate it into a sensor that is a crude sensor, very indirect measurement of the state of that system. So it's a hypothetical study. We selected that name, but I think you are very correct that this is ideal for processing sensor information.
Armen, thank you for this excellent talk. I feel very fortunate to have learned from you and to understand better your research. I'm very curious about the decision-making aspect, in particular within the context of large-scale systems and the role of uncertainty. So let me be concrete now. So it's easy to imagine that these Bayesian networks can have hundreds, thousands, tens of thousands of nodes in these large-scale systems. And I'm curious about how uncertainty and error would propagate. So, clearly each component, there's some uncertainty associated with these probabilities that you compute, and as information gets propagated through the network and you want to evaluate, for example, the value of information to justify an inspection, you compute the expected value, but I'm curious about the second moment now. And when you have these large-scale systems, is the variance just so high that it's difficult to trust even the expected value?
Well, of course, the inference diagram, this decision theory, is based on the von Neumann Morgenstern theory of decision making. That is, you maximize the expected utility. If you don't believe in that, well, there are people who don't, but that's what decision theory does. And it says that if you don't go with maximizing expected utility, in the long run you lose. Insurance companies don't do this. Insurance companies operate differently. So it is possible that you could manipulate that by how you assign your utility functions to various states. Regarding errors, of course, any engineering model we have, has errors. What do? We try to incorporate the error, account for the error, in which case it's very easy. All you have to do is add one more node with the error as a parent to that node. But engineering decision-making is the ultimate responsibility of engineers. It's the most difficult the task we have as engineers. And often you have to make decisions based on models and accounting for the error. And then what you do is you look into the sensitivities. There are issues that you're not sure. You want to make sure that your decision is robust relative to the parameters, or at least you have accounted. If there's high sensitivity to a parameter, you make sure you have accounted for the uncertainty in that parameter. So these are the tools that we would use to make sure that our decision is not inappropriately sensitive to a parameter that we have neglected to properly model. And so these are the kinds of things I would do.
It strikes me that in these large systems like the one you described, there are, in order for this system, in order to construct this model, there's a lot of numbers that you need. And many of these numbers are probabilities associated with very rare events. So can you say a few words about how you can populate all of these matrices with numbers? Where do you get them?
Well, one advantage of Bayesian network is that the information you need are all conditional. So in the first part, the seismic hazard part, the kind of information you need is exactly the kind of information that we use today for seismic hazard analysis. Distribution of magnitude, whatever seismologists and earthquake engineers have fairly good handle over that. So that's, say, if you have to populate the conditional probability table for the test likelihood, then that comes as a package of that test. If someone gives you a machine and says, if you put this on this bridge and do vibrations and will tell you what the frequency, natural frequency of the bridge is, they have to tell you what is the error in that measurement. And that gives you that conditional probability. So it comes in these bits and pieces. This is putting together a lot of things that we already do. You know, this test likelihood is something that people use whenever, if you have any indirect measurement, you have to use that test likelihood metrics to assess the uncertainty in your observation. And so that's where you get. The framework puts all these things together. That's what it is. But I agree with you, there's huge amount of constructing something like this for the, say, water distribution system in Berkeley or in the Bay Area would be several years of work maybe. But once you have it, then it would be a very useful tool.
Armen, I was curious, so you beat the memory. The memory was going exponential, so you made that go linear, but then you turned it into exponential compute time. All right, so what are the prospects for dealing with that? Because if the compute time is exponential in the number of components, it's obviously somewhat limited. So what are the prospects for beating that part of the problem?
Sanjay, I sort of briefly mentioned that this is the crude part. Then Iris has developed heuristics that drastically reduce this. For some examples, actually, it goes up linearly. But it depends on the topology of the system, of the infrastructure system. And yes, now with this, probably we can do several hundred components. For example, one of the heuristics, not heuristic, it's more than heuristic, it's which we didn't do here. Any system is made up of subsystems that are series or parallel. So we collect all those series systems we represent as one component. Any parallel subsystem is represented as, we call them supercomponent. So there's that reduction happens, and there's drastic drop in sense. But having said that, I don't think these approaches yet are capable of being scaled up to, say, thousands of components.
So what you describe is almost like what we do in multi-scale modeling of composites or something, where you take the fine scales, you coarse grain them, and you move up.
Yes, in fact, we've used the word multi-scale modeling of systems.
Armen, thank you for the great presentation. These systems usually have redundancy and dependency or strong dependency of one component on the other. I was a little surprised with the results that it shows when evidence 4 came in. I think it was component 17 or something, had a probability of failure of 1, which consistent with the information. But I don't see other components also have this very high probability that may have strongly dependent, its failure depended greatly on the failure of this component. Was this because of the nature of this example, or this is something not addressable by this method yet?
Yeah, well, in the example, Michelle Bensi did the example. She assumed statistical independence between capacities of the components, which I think is reasonable because one of these components, for example, is an aerial bridge, the other is a tunnel, the other one is a embankment, and so on. So I think it's a reasonable assumption there. But there's nothing to prevent us from doing dependence between. Of course, the states of all the components are dependent here because the demand is dependent.
Not the capacities.
Not the capacities. We assume the capacities to be. But you could easily, if there's any reason to provide link between them, you can.
I'm here.
Yes, thank you for the great presentation again. In my experience, uncertainties are very much, do have a very great influence on your model and your results. Now, there are also uncertainties within uncertainties. In other words, the uncertainty that you pick could be related to the variability of the parameter, but it also could be related to the state of the parameter. So it could be state dependent and it could be parameter dependent. Do you consider these kind of influences as well?
We can. We didn't do here, but we can. For example, I had a distribution of earthquake magnitude which has that distribution has certain parameters. In reality, I'm uncertain about the parameters of that distribution. So all you have to do is just add one more node as parent to it.
Then how do you decide what?
Well, then you have to do data statistics. You have to do Bayesian parameter estimation, get the posterior distribution of the parameters and put them there. So you can't create numbers from vacuum. You have to have data to create those. But the framework is very general. There are, as Sanjay pointed out, there are limitations in terms of how far you can go. Can I model 10,000 components? No, I can't. Can I handle 100, 200? Yes, I can. Memory demand is a hard demand. Once it exceeds, I cannot solve the problem, period. Years ago, when Michelle was working, I invested in a computer with 32 gigabytes RAM memory. At that time, it was huge. We found that we added 2 more nodes. We ran out of memory, so it didn't work. On the other hand, maybe you can sit for 2 days and do computations if you're willing to do it. Or maybe you do parallel computing. You do cloud computing. So there are other ways of handling it. But memory demand is really hard demand.
Over here, how do you ensure that maintenance of your sensors will be maintained during various epochs of the political administrations? I mean, I think Fukushima, they shut down their sensors. Maybe I got that wrong.
To be honest, I'm not the right person to answer that.
I mean, it seems
don't have experience with sensors, but obviously, after an earthquake, if certain sensors don't function, you don't have the information, so you can't update, you cannot process that information. Of course, worse problem would be if a sensor malfunctions and gives you wrong information and you don't realize that this is wrong, and of course that would be really bad.
A false negative would be worse than a false positive.
Yeah.
It seems like you could possibly build in something to the system to perdure it 15 years, maybe some automaton, so that things would be, at least when devices shut down, they'd be automatically registered for some administration to go out and fix.
I'm sure you're right. I think probably these kinds of systems will become available. But I don't have expertise on sensor hardware, and so I cannot really comment on that.
Armen, I don't know if I can ask second question. If there's anyone who wants to ask first question, I'll be happy to yield. If not, I'll ask my second question. Anyone has first question? All right. My second question, Armen, actually relates to, again, collecting the initial information. As far as the word that you use, visual, I like to say, why not we use sensing data? Visual is one sense, and we can have other. But even if the data comes to you from either visual or instruments or all kind of reliable sources, still you will need another step before you use that data. That's what I feel. And that step should be, as you said, the last sentence you said to this gentleman, we have to see if this data tells me that there is damage, is that damage really consequential? Before I send it up as point 4 saying that, oh, something has failed. Why not have actual model, finite element model of the system built into a process before earthquake happens, and when the sensor says this column pier E2 of that bridge has cracks, that information should go to that finite element analysis, automatically put into that system, and see what that means. Is that damage really consequential, and you should shut down or reduce the speed, or that data is just one point on that bridge, and one crack on that bridge doesn't mean much to make that important decision of shutting down the system. So why not have the data from the field, have it pass through a high-powered computational mechanics to see what is the consequence of that physical evidence, and then, based on your, put it into your network.
Hassan, each of the component nodes have multiple states. This could be as many as one wants. Of course, the more there are, the more computation will be necessary. And these states, some of them are inconsequential states, some are more consequential. And in order to come up with these states, in fact, one would do an analysis beforehand, not afterwards. You would do beforehand, and you would come and say, if this, for example, you would say if the interstory drift exceeds so much, this is the state of this component, this building. Building is one component, or if the pier drift exceeds so much, then this is the state. So you would do this analysis beforehand, and it's all coded into this system. You don't want to do the analysis right after the earthquake. Right after the earthquake, you want to quickly make decisions on things like, should I send my rescue crew here or there? Should I inspect this component before I use it or not inspect? You know, these are the kinds of decisions, but you want to make them very fast. Yes.
Unfortunately, we have to make a decision to close this session. But the event is had not finished because we have a reception in the atrium area, and Professor Alvarez Cohen is going to offer a toast to celebrate Armen's great lecture. So please, you're all invited to the reception, and we'll see you there. If you have more questions to Armen, he will be there. So.
Yeah. Thank you.